So today I'll be here to introduce our new paper, FlexMem, adaptive page profiling and migration for tiered memory. This is a joint work with SK hynix. A tiered memory system has multiple memory components. The fast memory has higher performance, but slow capacity. We take DRAM as an example. The access latency is 95 nanoseconds, but the capacity is only 128 gigabytes. For slow memory, they have relatively bad performance, but have large capacity. For example, the optimal memory, the access latency is 345 nanoseconds, but they have 768 gigabytes. A lot of media is sector memory. They have 215 nanoseconds, but they can have terabytes level memory. Memory tiering has three key components. The first is memory access profiler. It captures memory accesses. Then, based on these memory accesses, it will classify pages as cold page, warm page, and hot page. Example is fault-based profiler or hardware event-based profiler. The second component is promotion. Hot pages in slow memory will be moved to fast memory. Fast memory access latency is much smaller than the slow memory. By promotions, fast memory accesses can be improved. The last one is demotion. Cold pages are demoted from fast memory to slow memory. It can make space for upcoming hot pages. We evaluate two recent memory tiering solutions, and we get the following observations. The first is about profiling method. We evaluate the TPP, which is using fault-based profiling, and MEMTIS, which uses PEPs-based profiling. This figure shows the execution time of two memory tiering solutions. The x-axis represents the workloads we used, and the y-axis represents the execution time. The lower is better. In FD and SP cases, the fault-based method performed better than the PEPs-based method. In these cases, the hot sets are changing quickly. PEPs cannot detect these changes timely, which will have bad performance. However, in other benchmarks, the PEPs-based method performed better than the fault-based method. These applications does not have quickly trained hot pages. PEPs is a better solution. So we got our first observation. Different applications actually prefer different profiling method. There's no single profiling method is a permanent winner. We also monitor the rate of page promotion failures. Most of these failures are because of the shortage of fast memory space. We test the TPP and Autoluma. Those two figures show the rate of page promotion failures. The left figure shows the TPP results. We found that on average 83% of page promotion failures. However, in Autoluma, we found that almost 100% page promotion failures. That's because Autoluma does not have any demotion functions. So when the allocation finished, the pages in fast memory won't be moved. So we got our second observations. Page promotion failures happen often because of the shortage of fast memory space. We also monitor the page access frequency distribution trend to study the warm page set. This figure shows the page access frequency distribution of signal. This figure shows the beginning phase of the signal. Signal is an in-memory database application. We use PEPs to get the historical accesses and categorize the pages into multiple bins. Maximum is 16, based on this access frequency. The index of each bin represents a specific access frequency, and the height of each bar represents the number of pages in a specific bin. We got continuous 20 samples of the bins to study the trend. We only choose the former 7 bins since these bins are not hot bins. we found that 96% of the pages in bin 1 are shifting to higher bins within 2 simple intervals. 80% of the pages in bin 2 are shifting to higher bins with 3 intervals. This shifting is because these pages are continuing getting accesses, misclassify this page as code pages, and demote them will incur unnecessary data movement and overhead. And we also had the results during the middle phase and end phase of the signal. We found that this trend still persists. So we got our third observation. No single bin can effectively capture the warm pages. Misclassifying warm pages can incur unnecessary data movement. So based on these observations, we propose FlexMem, adaptive page profiling and migration. For profiling method, we propose adaptive page profiling to use best of 2 profiling methods. For promotion failures, we propose adaptive page demotion to reduce the page promotion failures. For warm pages, we propose an adaptive warm set based on runtime statistics. So let's first talk a little bit about PEPs-based profiler and fault-based profiler. This figure shows the workflow of PEPs-based profiler. When there is a performance counter event is captured by the PEPs profiler, it will update and record the addresses. The page in the histogram will be updated. The location otherwise be moved or still stay in the original bins. And then the hot pages will be promoted periodically. For pages with many accesses across the lifetime, PEPs can classify them as hot pages accurately. However, for emerging hot pages, PEPs needs long time to accumulate the access frequency. Emerging hot pages means the new hot pages in the hot area change period during the application execution. For fault, now let's talk about the pneumo fault. If there is a page, then the pneumo fault is set. And at the same time, that the page is already in the active list. Then it will have the opportunity to be promoted. Here, a single page fault could incur a promotion for emerging hot pages. However, it could be too aggressive to promote pages because there's just one single page fault. So FlexMem will combine the performance count-based method and fault-based profiling method. Both profilers are utilized to get both advantages. To avoid the disadvantages, FlexMem will coordinate those 2 profilers. So coordination is needed. FlexMem will disable all the independent promotion functions of 2 profiling methods and only maintain 1 promotion agent. This promotion agent will select suitable candidates from both profilers. There's more details in the paper about how to select the promotion candidate and how to control the overhead and also asynchronous migration. So now let's talk about page demotion. Page demotion currently, how to do page demotion is, there is a demotion watermark. If the memory consumption is large than this watermark, then the demotion function is invoked. The demotion function will demote pages to make the memory consumption less than the demotion watermark. Existing works use a constant watermark to invoke demotion. However, when fast memory have many code pages, using a constant demotion rate could incur slower page exchanging because there is no available fast memory space. Here, in this figure, we show a very simple example. Suppose the demotion just demote one code page could satisfy the demotion requirement. However, there is many hot pages in slow memory are waiting to be promoted to fast memory. In this situation, because the demotion watermark is already satisfied, the hot page will have the no memory in fast memory error. So the promotion failure will be generated. FlexMem will dynamically decide the demotion rate and runtime. 3 pieces of information are considered. The first one is classified code pages in fast memory. This information can be get from a profiler. The second and third information is a promotion failures by either PAPES or page fault based profiler. We have an equation to calculate the demotion rate in the runtime. By this equation, the demotion watermark can be changed. The demotion watermark can be moved left if there is more code pages in the fast memory, or there is more promotion failures in last period. And it can also be more right if there is fewer code pages or promotion failures. So now, let's talk about adaptive warm set. Warm pages is a category of pages between cold and hot pages in terms of the access frequency. Warm pages are highly possible to be hot in the future. Keeping them in fast memory can avoid unnecessary page migration. To decide the right warm page set, FlexMem will monitoring the page shifting between continuous bins, because it will have very high overhead if you want to scan all the pages. FlexMem will update the one page range, the one bin range every single period. From current period to next period, we can monitor how many pages are in the specific bins that are moved to higher bins in the next period. By calculate the shifted page ratio, we can use a threshold to decide if this bin should be included in a one page set. There is more details in the paper. Now we'll talk about how to avoid the overhead and what is the algorithm. So now let's talk about evaluation. In the evaluation section, we want to answer 3 questions. The first, how does FlexMem perform with memory-intensive applications, such like HPC workload and in-memory database? Second, can FlexMem use fast memory effectively? The last one, can FlexMem address the existing memory management problem effectively? We tested on the Intel Xeon CPUs, and we limited the DRAM size to 30 gigabytes, and we use 768 gigabytes persistent memory. We test all NVMe setting, TPP, MEMTIS, and tiering 0.8. Here are the benchmarks we used. We use 6 real-world applications, and the working set size is ranging from 64 gigabytes to 133 gigabytes. These figures shows the overall performance that normalized to all NVMe setting. From this figure, we can see FlexMem perform best in all the benchmarks. In FT and SP case, they get the most performance benefits compared with other benchmarks. FlexMem outperforms tiering 0.8, TPP, MEMTIS by 32%, 23%, and 27% on average, respectively. This figure shows the fast memory and slow memory access ratio. From this figure can verify the benefits of FlexMem. FlexMem leads to more fast memory accesses and other solutions. That because firstly because of adaptive profiling, second about the adaptive demotion, the last one is about warm set bins. Here, to answer the question 3, we have a case study of Shin. Shin is an in-memory database. The left figure shows the memory access heat map. The x-axis represents the execution timeline. The left y-axis represents virtual address space. The right y-axis represents the access numbers. So from this access map, heat map, we see that most of the pages get continuing accesses. FlexMem identifies more warm pages than MEMTIS. The right figure shows the number of warm pages identified by MEMTIS and FlexMem. FlexMem by identifying more warm pages, FlexMem actually can reduce the demotion of the warm pages. So here is the conclusion. The key to address limitation in current memory tiering solution is being adaptive. The first is adaptive profiling method, using two profiling methods to get the best of two worlds. The second, adaptive demotion. Control the demotion rate based on the promotion failures. The last one is about adaptive warm bins. Avoid unnecessary page demotion. Thank you.